there's a pretty big typo here. This is a two-step reaction, meaning we have to first do the mercury reaction, and then we follow that with a step 2 of the sodium borohydride. Okay, so 2 steps, independent of each other. So, taking a look at the first step, okay, or the first part, where do we have reactivity? Okay. So I hear reference to the pi bond. What is the pi bond going to act as? An electron source. Okay. What do we need to find then? Okay. We need to find something that is positively charged or missing electrons. Okay. So we would go to the rest of our reagents and say, what do we have? Mercury is going to be really our only option. There's a lot of confusion over what OAC stands for. Okay. AC stands for acetyl. The acetyl group is a carbonyl with a CH3. If we have OAC, you now have this structure. Okay. So what we're saying by that is that we then have mercury bound to the OAC, and there's now 2 of them attached. What type of bond do we have between mercury and oxygen? An ionic bond, which means those electrons spend most of their time with the oxygen. If the oxygen takes the electrons, what happens to mercury? It becomes positively charged, which is exactly what we needed to find to react with our alkene. Okay, so there's a potential positive. Do we have a positive in water?
No.
There's a partial positive. Okay, which one's more positive? Mercury, because ionic bond. Okay, that is going to be generating our larger positive charge. So the mercury right now is a better option. THF, everybody seems to freak out at this, and I understandably so. THF is purely a solvent. Okay, it's not doing really anything in the reaction except making sure everything mixes. That's it. Okay, so we can ignore the THF. So at this point we've got our mercury with the positive. That can react with our alkene, kick out the OAC, and now I'm going to clean everything up here so I can draw it a little bit cleaner. Right. Is there a difference between those carbons? So if we're making our bond to our mercury, does it matter which bond I make?
No.
Why not? It's symmetric. Okay, so no big deal on which one I use. Okay, so let's just say it's from the bottom, then have the OAC up here. Okay, and now we run into an interesting dilemma. What else would I need in this structure? A charge on that carbon. Okay, the other carbon needs to be a carbocation. For those of you drawing this out, stop. Okay, what do we know about mercury?
Doesn't change anything. No rearrangements.
Yep, no rearrangements, but why? It comes back to what we know about mercury. Yeah, it's an electron shuttler. Keep going. Periodic table may help. Transition metal, I can accept that. Keep going. It's a nucleophile and an electrophile. It's a liquid. It's not going to be a liquid here because it's actually attached. Where's mercury? Where's bromine? What did bromine do when it reacts with an alkene? Made a 3-membered ring. Why?
It's huge.
It is huge. Bromine or mercury is bigger than bromine. What are we going to expect to have happen? The mercury is going to block that positive position, and we end up not forming a carbocation. We end up forming a mercuronium ion. And this comes from the reactivity of the mercury, okay, which was addressed out in the audience just a little bit earlier. Okay. Mercury acts as an electron source with a lone pair of electrons, okay, and as an electron acceptor with the OAC leaving. Okay. What's that?
Does it second acetyl.
Not super critical in deciding that, but yeah, it's typically shown on there. If mercury gains electrons and loses electrons, okay, we end up picking up a positive charge on our mercury. Because it's gained one set of electrons and it's lost two sets. So we've got that positive charge. What is now special about this structure? It's charged. Mercury, formally charged, which is problematic, and three-membered ring. Three-membered rings, are they particularly stable? No, so they want to break open. Mercury, does it want to be positive? No, so it wants to grab electrons back. Okay, so with the existence of a three-membered ring, which I'm just going to call a three-ring, and a great leaving group, okay, this reaction is primed to be attacked by a weak nucleophile. Okay, why would we expect it to be a weak nucleophile as opposed to, say, an electrophile? Mercury wants to break off, meaning it wants to take the electrons with it. As it takes those electrons, what charge builds on the carbon? A positive. So what do we need to find? A negative, i.e. nucleophile. So we go back to our reagents and say, do we have a nucleophile in there? I won't quite accept OH. We've got water. Okay. The water is present because it is acting as a nucleophile. Those lone pair electrons can come in, whoops, come on, do a backside attack to generate our new species with our mercury, OAC, our OH. Does oxygen, or what's the thing missing right now? Positive charge on the oxygen. Does it want to be positive? What does it do? It takes the electrons away from one of those hydrogens, and we end up with neutral OH. Okay, it started positive. So we've done everything we possibly can in the first step. Okay. The mercury came in as our primary positive, reacts with the alkene to form a very unstable reactive structure. Water, as a good nucleophile, can come in, break that structure open. At this point, I now have a mercury-carbon bond. One of the reasons why mercury is particularly toxic is that although it is an ionic bond, it tends to stick relatively well to carbons. Okay? So that bond is going to stay there until we can force it off, okay? Until we can really break that apart. How can we break that off? This is where our second step comes into play. So when we move to our second step, we have to evaluate the reagents we've got. You'll notice that they wrote out ethanol. Sometimes if they write out the salt or write out a name of the compound, it's typically the solvent. So again, we can kind of ignore our ethanol, at least loosely. We then have to evaluate what sodium borohydride is supplying. Okay. The first thing you should see is we have sodium, which is a metal and ionic bond, which means that splits, and we're really looking at BH4. And BH4 is going to carry a negative charge. Okay? So we want to evaluate the reactivity of that. While boron is negative, does it have a source of electrons? The boron itself doesn't have a source of electrons. It would need a lone pair to act as a source of electrons. Okay? Boron is perfectly happy to be all by itself. BH3, which is a bit weird because what is special about that structure? It doesn't have its octet. Boron is one of those exceptions that can be under its octet. The other one? Aluminum. Where is aluminum relative to boron? Directly below it. They have the same chemistry associated with them. Okay? That then, yes. That then means we have a potential for hydride chilling out. Okay? So we've got boron that could act as a potential partial positive because it has an empty p orbital, and we have that hydride. what ends up happening? The boron can coordinate loosely to our mercury. The hydride can coordinate to the carbon. The result I get an OH and an H added across the double bond. Okay? So your final answer is just the addition of H and OH. There are 3 reagents. Oh, I'll come back to that in a second. Questions about that? What was your question? You good? Yes.
Well, actually it doesn't matter because you're adding. Is that a syn addition or an anti-addition?
So deciding syn or anti on this is complicated because it goes through a variety of mechanisms in it. Your water will attack backside, so the addition of mercury and OH are added anti. Okay. The question then comes in is how is the hydride attached? Okay. The hydride ends up coming up with a variety of mechanism. Typically is added on the same side, but it's on the same side of the carbon-mercury bond. So you end up getting a weird mixture of products coming out of this, which is interesting because if we look at the product I've got shown, do we have a stereocenter? Yeah, we do. And you'll notice that I'm not specifying whether it's wedged or dashed. We get 2 products. We get an enantiomer in this case. If we have 2 stereocenters in the course of the reaction, we end up with a big smattering of products. It is a complex enough mechanism that you do not get tested on it. Okay? You are responsible for knowing that the mercury reagent with borohydride adds H and OH in a standard fashion, if you will. Okay? Or heaven forbid we use the name Markovnikov addition. Okay? The hydrogen and the OH get added in your kind of standard format. In this case, there is no Markovnikov or anti-Markovnikov because both positions have the same substitution patterns. Okay?
So isn't there another, not the mercury, but I think it's like boron for the first step?
Wait, that was not the button I wanted. Dude, I completely deleted the picture. Really? So the question I was then going to ask, but I guess since you beat me to it, I'll have to answer it. Are there other ways to get the same product? Yes. Okay. One of those methods we just discussed was the 2-step result of mercury acetate in the presence of water. THF is kind of a solvent, or is a solvent, so not super important. It may show up, it may not. Followed by sodium borohydride. Again, you likely won't see the solvent. Second method, okay, is what Jennifer was just suggesting here, is looking at our borane BH3 followed by peroxide. If you go through and look at the actual reagents, they almost always list BH3 in the presence of THF, and they almost always list peroxide in the presence of hydroxide. Okay. I tend to focus on the BH3 and the peroxide because those are really the reactive ones, at least in my shorthand mechanism version. So what ends up happening? We're going to get the same type of chemistry that we saw in A. I mean, boron and boron, right? Right? They're both borons. Is the chemistry different?
Yes.
It's pretty drastically different. In A, that sodium borohydride is acting as H minus, giving us a nucleophile. In B, that BH3 species is really acting as a boron positive. It's acting as an electrophile. Okay? It's a little bit trickier than that because not only does it act as a positive, it acts as a hydride nucleophile. And we'll look at that when we look at the reaction. So, what happens? The borane comes up and reacts with our double bond. So the electrons from our pi bond come out and react with the boron. If we think about just drawing out a simple product from this, okay, again, be careful drawing this. We form our carbocation. What is the issue with our boron right now? What charge is it? Negatively charged. It has an excess of electrons. We now have BH4, the equivalent of BH4. What happened when we had BH4? We dumped out a hydrogen nucleophile. So when we now look at the structure, what do we now have? A hydrogen nucleophile. Can hydride exist off on its own? No. So that hydrogen must get kicked out and immediately absorbed by the system. Well, what would need to absorb that negative hydrogen? The carbocation. That reaction happens so quickly that when we look at the mechanism, we combine it into a single step, and the result we end up getting would be something along those lines. Yes, Troy?
There's no rearrangement.
There is no rearrangement. Okay, same deals with our mercury. We never form a carbocation for long enough to do anything with. So you cannot do a rearrangement. And in this case, how is the addition occurring? That hydride cannot exist for any significant amount of time, which means it needs to get picked up immediately, which means syn addition. The boron and the hydride are added to the same side of the double bond. Okay? This was something that we skipped over in class, and I may end up regretting it, or already end up regretting it, is that what do we now have for a structure? I know it's a vague question. Is this structure still reactive?
No.
Yes. What is it still reactive as? It's got the boron, which can accept more electrons from another nucleophile. Do we have more alkene? Yep. Yep, we do. So a second alkene can react. And what will end up happening is we will repeat the cycle that we just went through and did. I'm glad we picked this as a structure. It's going to be virtually impossible to draw. There is no sigma rotation here. Well, sorry, yes, the sigma rotation about that bond. Yeah, doesn't matter. So we end up with generating a structure along these lines where our boron has now been completely deprived of all of its hydrogens, and we now just have the carbons attached. Okay. That being a stronger bond will actually stick, and we can't transfer those carbons onto other carbons like we did with our hydrides. Okay. So we have a steric hindrance preventing this now new boron compound from dumping these carbon structures into the alkenes. Okay?
Now, in the case of B, you add the peroxide in order to stop that?
The peroxide is not added actually to stop this. This will happen. As soon as you add BH3 to your alkene, this is what happens.
Oh, really?
Yep. You go all the way out. Yep. Okay? We can't stop it at any individual position. In fact, I believe it becomes more active by doing the alkyl substitutions. So that then begs the question, what should our ratio of our reactants to alkene be to start with? Well, if we know boron will react 3 times, I can use 1/3 of the amount of that reagent, right? Because it can react multiple times. So we end up using a little bit less of the boron reagent when we go through and do this reaction, okay? Because we can. Okay? So if we said did this in lab and we asked for a % yield calculation, it would really suck. because you don't have a 1-to-1 ratio anymore. You'd have to be aware of the 3-to-1 ratio to do your limiting reagent calculations. Okay? The reaction now stalls here. There's no more reactivity that we can get out of it. And that's when we add the peroxide. How does the peroxide end up working? Okay, well, for sake of argument, I don't want to draw that big nasty thing again, so I'm going to erase all that. There are a variety, or your textbook has a much more detailed mechanism of how the peroxide is functioning. I would argue it's doing way too many complex things, and I think it makes it more difficult to understand. As long as we get to the gist of the point, which we'll show here in a second, any real mechanism is valid. Okay, which I'm sure there's organic chemists listening to this video now rolling in their graves. Or maybe in 50 years I'll listen to the video and roll in my grave. I can't believe I said that. Okay. So, what does our boron act as? Electrophile. Where do I have electrons? In our peroxide species. Those electrons can donate down to the boron, but now what happens to the boron? It becomes negatively charged. Okay? So what does it want to do? It wants to kick out a group. And remember, we don't have hydrogens anymore. These are all our carbon structures. So what does it kick out? One of the carbons. But now that carbon's coming out is a negative. Ooh. It needs to pick up something really, really quickly. What can it pick up? It can actually pick up the oxygen. You're going to say, well, doesn't that have a whole bunch of electrons? What was special about the peroxides? That is an exceptionally weak bond. Once one of those oxygens starts to share electrons, it now starts to become positively charged. Does it want to be positive? Nope. So it can steal electrons from the peroxy bond. The net result is that we now have our OH attached, and to our boron, what did we end up doing? That one step was a substitution through a big, nasty, ugly mechanism with tons of arrows. Okay. Overall, beginning to end, what did we do? An addition. We added an OH and a hydrogen. Okay. The next feature that goes back through this is let's evaluate how our H and OH, or H and our bromine were, or boron were added. Let's say they were added on the up face. So boron came in from the top, the alkene came in from the bottom. If I do that, that means the hydrogen over here, I'm glad I have lots of space, is wedged, which would then mean the boron was wedged. Remember, the boron and the hydrogen have to come in from the same side. Otherwise, you're generating a hydride nucleophile that can come around from the backside. Can't do that. When we go through and do the next step, well, nothing happened to our hydrogen that was added, so it's still wedged. Where's the OH now? Where is the OH reacting? From the boron. Is it coming in from the back side of that carbon bond? No, it's being added the same way we added the borane reagent, in a syn addition. Which means the OH stays wedged. We end up with a full-on syn addition of H and OH across our double bond beginning to end. Okay, which is tricky. We're doing multiple steps. We would figure there's no way in hell it could end up on the same side. Okay? But because of the reactivity of our boron, that's ultimately driving the addition to always happen in the exact same location, which is why we get the syn addition. So when it comes to the test, will you get tested on that? Abso-freaking-lutely. Okay, they will ask you, draw multiple products and show an H and an OH being added syn or anti. You need to be able to look at it and say the anti one does not happen. It has to be a syn addition. Okay? So
if the reaction happens properly, is a secondary product be
OH3.
When the reaction processes all the way out, one of the things you end up with is B OH3, or a version of it. It's borane or borate, or borax, I think even. Okay. And yes, that structure ends up being relatively stable. The oxygen is willing to share electrons easily enough with our boron, and we end up forming a pretty stable structure. What?
Borax is an equivalent to what?
It is a cleaning agent. It doesn't make it less stable or more stable than this. Okay. So, big lesson with our boron, we add the H and the OH. Next big lesson with this, syn addition, next big lesson. It actually adds the hydrogen and the OH the opposite direction of the mercury reaction. Why? In our mercury reaction, the water comes in and attacks the most substituted position. Okay? In the boron or borane reagent, what ends up coming in and attacking the most substituted position? Hydride. Okay, so we end up doing a swap in the chemistry because we have a different positive and negative. If you follow the positives and negatives, you can get the product correct. Okay? Last way. What are we adding across the double bond? We are adding hydrogen and an OH. Okay? Hydrogen on its own would be H plus. OH on its own would be OH minus. Can I ever do a reaction where I add those two at the same time? No, why not? They cancel each other out. Strong acid, strong base, can't do that. Right? So I could put them together, and I'd end up with H2O. The issue with H2O is that it is not reactive enough with the alkene. The alkene will not pull a hydrogen from H2O because we end up forming a negative oxygen. We'd end up forming hydroxide, which is an unstable species. So how can we get the alkene to react with water?
Two-step with acid base.
Add acid. Okay. It is still one step. We just add water in the presence of acid. It'll go ahead and do it. We'll do the acid-base reaction first to form the carbocation. The carbocation can then react with the water, okay, to add the OH. The issue with step C, or option C, you form a carbocation. Carbocations rearrange. Okay. All three reagents do the same overall thing, H and OH. Okay. C does rearrangements, B goes syn addition, but then non-standard addition. Okay. And then A gets us a standard addition, H and OH, in a complex stereochemistry system, so we end up ignoring the stereochemistry. Okay? Questions about that? Okay. So let's pause for a second. Okay. Multiple ways to go through and start this. Process I would start with would be draw cyclohexanol and sulfuric acid. So, now that I've got those two drawn, stick my hand into one of those. Which one am I going to scream about? Sulfuric acid. So my very first step should involve neutralizing the acid. What is the acid supply? H plus. What's going to neutralize the H plus? The negative charge from our OH. Okay. That should be my very first step. Loss of OH minus. Well, loss of OH minus is saying I'm taking the bond and breaking that off. Okay. Which would be the formation of hydroxide. Hydroxide, which is a strong base, in the presence of sulfuric acid, not a good option. So that means A has to be wrong. Loss of H plus by the alcohol. Okay, well, loss of H plus by the alcohol, what that's saying is that I'm taking the electrons away from the hydrogen. Well, oxygen's more electronegative than hydrogen, sure, that makes sense, but I'm then saying the alcohol is more acidic than sulfuric acid. No, that doesn't make sense. Okay. Formation of a sulfite ester. I don't even know what that means. Protonation of the alcohol. Hey, I did that. I'll put the proton on, so I'll stick with that. It's kind of a lie. I know what the sulfite ester is. Okay. What are they saying by a sulfite ester? Secondary reactivity of sulfuric acid. Okay. Primary, I agree, acidic. What's the secondary chemistry? Why are the hydrogens acidic? Electronegativity of the oxygens. Are the oxygens connected to anything other than hydrogen? Sulfur. What does that mean happened to the sulfur? What was that? It is partially positive. Do I have a negative somewhere in solution? The oxygen could theoretically attack the sulfur to form a sulfite ester. How likely is that? Pretty horrible. Okay. That would mean sulfuric acid is acting as an electron acceptor. It's still acting as an acid, Lewis acid.
Wouldn't still be pushing off an OH though.
Even if it ejected in OH, that's a secondary step. Okay, kind of makes sense? So, your first step, what did I do? Draw it. Stop thinking in your head. Okay? Very bad place to be. Write it down. Okay? When it comes to the exam, I have tons of what's that, tracing paper. Okay? So you will have tons of tracing paper that you can use. Okay? I will give you tons of scratch paper that you can use. I will give you a blank. Actually, before I delete that, questions about that? See-through paper, yeah. So I'm going to say that's no questions about that. I will also give you a piece of paper that will list 1, 2, 3, 4, etc., all the way through to 70. And next to those, I will have A, B, C, D. If you go through the test and you don't know what answer is correct, but you know what answers are wrong, I don't want to use A. Now when you come back and look at it, you'll be like, oh, A is the wrong answer. Don't look at A. You already know it's wrong. Look at the other ones. Okay? You can shorten the amount of work that you have to go through and do by writing that information down. You are not allowed to write on the test, but you need to write down. Okay? So write down on the scratch paper. Use everything I give you. If you don't want to use it, that's fine, and you want to work in your head, great, you're a genius, fantastic, good job. Okay? But when your exam comes in low and I'm trying my best to get you more points, what I'm going to be looking at is the work that you wrote down. If you give me no work, there's nothing I can do to help you out. Okay? Make sense? It's a question?
No, that was my question. If you can write on the test.
Yeah, you can't write on the test. Okay? So, 22. Actually, I think I can get this one. Everybody's sick. Let's do this at home. I can even see what I'm pointing at. That's 23. 22. Let's erase all that. What is the stereochemistry of the nitrile produced in the reaction below? What type of reaction occurred? just the type of reaction,
Substitution.
substitution. Are there different ways substitution reactions can occur?
Yes.
Yeah, those would be known as our mechanisms, which would be SN1 and SN2. I think it was you, Sean, said it's SN2. What about this reaction tells you it's SN2?
CN is a strong nucleophile.
You go through and look at your active reagents. Sodium is a metal, which means really what you're looking at is the nitrile with a negative charge. The negative charge is a strong nucleophile. Strong nucleophiles favor SN2. You should evaluate all other information just in case. Okay. Do they give you the solvent? No. Do they give you a leaving group? Yeah. But you needed a leaving group anyway for both mechanisms, so that's not helpful. The last thing we could evaluate would be substrate. Okay, so we look at our substrate, we identify our leaving group. What was our leaving group? The OTS. So we want to look at our carbon and say, what is that carbon? It is connected out to two carbons, so it is secondary. What do we know about secondary carbons? It's a pretty crappy reagent to see because they do everything. SN1, SN2, E1, E2. Okay, which means looking at the substrate didn't help us. The only clue we've got to work on is the nucleophile. Okay? Because the nucleophile is strong, we're running under SN2 conditions. SN2, the very first word that needs to come into your head is exactly what you just shouted out back there. Well, mumbled out. Backside attack. Okay? So that means our nucleophile needs to come in from the backside of our leaving group. Our leaving group is located to the down and to the right, which means our nucleophile needs to come in from the up and left side. When the nucleophile comes in and attacks there, what happens to the other groups? They get pushed the other direction. The result is that I would end up with CH, go away, CH3, H, and then my cyanide. Okay. And I've done my backside attack, everything looks good, I've now got my answer. I'd be like, yes, I drew a beautiful structure, crap, none of my answers have structures. Oh well. So you can either be excited and count your small victories that you drew it out and you're happy with it, or you could have jumped to looking at your multiple choice answers to evaluate a little bit closer. What is the complication of doing a backside attack? How many products do you get? One. Only one product comes out. That is why I drew only one product. Okay. What happened? It typically goes through inversion in stereochemistry. So if I start with S, it's become R. So I could, if I'm in a rush, go through and box in R. If I got a little bit of time, what should I do? Verify it. Okay. Go back and look at your structure. We're comparing carbon to carbon. That's a bad color. Let's do, we can do blue. Carbon to carbon to carbon to hydrogen. Hydrogen is 4. Between the carbons, I can't really tell a difference. Okay. This is where I would need to look at the Lewis structure for the nitrile. I have a triple bond to the nitrogen, meaning that to that carbon I have 2 phantom nitrogen bonds and 1 regular bond to a nitrogen. So when I go out to that group, I encounter a nitrogen. To the other ones, I encounter hydrogens. What does that mean? Sorry, I just completely lost track of what I was doing. We've got number 1. If we go out to the other positions, or carbons, I did catch up with you eventually. Okay. If we go through and evaluate the other ones, they go out to hydrogens or carbon. Either way, nitrogen is a higher priority than carbon because I think it's, did we say it was mass? I always forget.
The book says it's mass.
It's mass. Either way, in this case, we're still correct. Okay, so if we go based off of mass, nitrogen is still heavier. So our 1 priority is correct. The next 2, whoops, that's a 3 Oh, man, fine. 3. So 2. Yeah. I'm catching up to you. And 3. When we go through to connect, we go from 1 to 2, 2 to 3. I'm going which direction? Clockwise. Okay. I would probably write clockwise down, which would then say R. The reason for that is I personally am horrible with understanding clockwise and have definitely led students astray on that. So I need to check it multiple times to verify that that is indeed clockwise. That says R. Before I finalize my answer, I want to make sure that my lowest priority, number 4, is indeed dashed, and it is, which means my answer is the R isomer only. Make sense?
When you do backside attack, you only get one product.
Backside attack will only get you one product. Okay. Why? It all happens at the same time. Okay. That's why you only get one product. For SN1, why do we get 2 products? Not a backside attack. It happens in multiple steps. With multiple steps, we increase the likelihood of one of those reactions happening in different locations. Okay. Make sense?
So for an SN1, you need a base rather than a nucleophile then?
For SN1, what do we need? How can I make this reaction SN1? I need a weak nucleophile. So I could change it to say water. Questions about it? What am I looking at? Close enough. 25. Which reaction would produce phenylpropyl ether? Oh, you're just trying to be annoying. Phenyl? What is a phenyl group? It is a benzene ring, okay? Not to be confused with cyclohexane, okay? 2 drastically different structures. Okay? The phenyl means I have something attached at that position, so there's my phenyl. Okay? Then I say propyl, so I might start to then say, well, I need to attach a propyl there, but then it should end the name. Oh, that's because I'm looking at an ether. For it to be an ether, what does that mean that X needs to be? Has to be an oxygen. For it to be the propyl, I then need 3 carbons coming off. This is something to be very cautious on. Make sure you actually draw out your 3 carbons. Okay? Very typical for students to go through and just say, oh, well, that's my phenylpropyl ether, because I have that little bendy thing, so it's a propyl. No. That's an ethyl attached to an oxygen. Okay? So we now have our phenylpropyl ether. We're looking at a reaction that's going to produce that structure. So by looking at our final product, we could start to evaluate bonds that would be likely to make or break. So if we were going to make this structure, what are the 2 most likely bonds to evaluate?
The carbon, our counterweight carbon chain.
Okay, so, oh, I think a lot of you are going through and looking at the answers, so let's clear that up. In that structure, which are the bonds that are most likely to have been made? We're looking at the bonds between the oxygen and the carbon. Those are the most likely bonds to have been made. Why? Those are our largest difference in polarity, our electronegativities. If we were going to say break the purple bond, where would we expect those electrons to go? To the oxygen. So I would expect the oxygen to come in as a negative and the carbon to come in as a positive. Okay. You say carbocation, and here we've got to be a little bit careful. Oh, I know why I wanted colors. Why do we want to be a little bit careful there? What kind of carbocation would that be? a primary carbocation. I can't form a primary carbocation. Okay? So what if it was partially positive? Sure, then I could run an SN2 reaction, okay, instead of doing an SN1. So what I'm looking at is which bond is most likely to break, how it's likely to split, but then evaluate, well, what mechanism is it going to run under. Okay? So I have to be careful in applying each of those systems. If we go through and look at the blue bond, how is that likely to split? Okay, same deal, negative and positive. Okay, and I'm hearing a not really. What do you mean not really?
I thought because the benzene is so stable and because it's an sp2 hybridized, it doesn't have the SN or doesn't leave. Like
Forming a carbocation on a benzene ring is a massive no-no. We can't do it. Okay? But just like with the other one, we had forming a positive carbon on a primary, which we said was also a massive no-no. Okay? So what does that suggest about the mechanism? It has to be SN2. We cannot do it SN1. Neither of those options are going to give us a good system. So what we need to be looking at is potentially a partial positive for both of those. What does that suggest about our negative? Careful. SN2 needs a strong nucleophile, which means full negative charge. Okay? So now let's think about it. Okay? If I have a partial positive, can that negative, partial positive, let's look at the blue one, could I have that negative oxygen come in and react with it? In an SN2 reaction, where does that bond form? Backside attack. Where's the backside of that bond? Through the middle of the ring, which you're suggesting should not happen, rightly so, because steric hindrance. So what does that mean? It's got to come in the other way. So the answer I am looking for is the one where I have a negative oxygen reacting with a partially positive carbon. Make sense?
So the purple bond is forming your reaction.
The purple bond is the one that's going to be forming our reaction. So now I can go back and look at all my answer choices. Now I've gone through and erased all that. Okay. Notice in our answer we said we need a partially positive carbon on the propyl part. The oxygen should be formally attached to the ring. Answer C and D. What is problematic with those? Bromine's not going to leave. I can immediately eliminate answers C and D. Okay? Which means I'm looking at B and A. Okay? So B and A both give me the negative oxygen part. Do they both give me a propyl with a partial positive charge? Which one doesn't give me a propyl with a partial positive charge? So carbon, when bound to oxygen, is not partially positive. We can address that. Do I have a partial positive?
Yes.
Yes. Both of these reagents would suggest to work. What are you suggesting eliminates answer choice A?
The hydrogen would come off and so you'd have a negative.
I also have a positive hydrogen. When I run this reaction, how many positives do I want? One. Only one. If I have multiple positives, what happens? Multiple products. A is not a good option because I have multiple positives. That could mean multiple different products coming out of this. That's going to mess with my results. So I don't want to do A for that reason. Okay, we can get more specific on that in just a second here. That would then suggest B is our best answer. What reaction does occur? What is the product that I would expect to find when I react A? Because this is a common question as well. What's that? What is the H going to react with? the basic oxygen. And we end up with not an alcohol, for those of you who keep saying that. We have a phenol, not to be confused with phenol. Okay, oh well. Questions about that? Yes?
For A, could you also see that as if between the carbon, oxygen, and hydrogen, the carbon and oxygen bond is more, the carbon is more electronegative than the hydrogen, so that bond is less likely to break between the carbon and oxygen.
Which is what we're showing here with this final product, yeah, exactly right. The hydrogen is going to be your larger or more reactive positive. Okay? Kind of makes sense? Okay. Where are we? 26. Reflections. What is the expected product of this reaction? This one's tricky because we actually haven't talked about that reagent. I think you guys should be able to do it. This is a potentially valid question. For this version of the exam, it would for sure show up on the next one, or for the full year. So what do we see? Three-membered ring? What does that three-membered ring tell you? It's more reactive, three-membered ring. I want to break that open. So our three-ring needs to break. It will break at one of those positions to the oxygen. Why those positions and not the one between the carbons? What's that? Oxygen is not positively charged. Oxygen is more electronegative. The difference in electronegativity between the carbon and the oxygen is causing those bonds to be polar. Those two need to be my key bonds to focus in on. Okay. So I want to break that structure open, okay, where my oxygen will leave as a minus. So it's going to start collecting electrons, and that means my carbons will be positive. So what am I looking for to react this with? A negative. So I now need to look at my reagent and say, do I have a negative? Okay. THF is our solvent, so we can eliminate that. We then have LiAlH4. Oof. I haven't really seen that. An ionic bond, okay. We can break off the Li, and we'd end up with aluminum, H4 with a minus. Aluminum, right underneath boron. Guess how aluminum reacts? The same way. And we could evaluate the bonds between aluminum and our hydrogen as ionic bonds. Please don't lose connection.
Where are you writing?
Yeah, it's lost its connection.
So is D a bigger group than CH?
Give me a sec here.
D is deuterium.
Okay, with our H minus. Okay. As Corey was suggesting, it's still an ionic bond. So really what this reagent is supplying is H minus. Okay. That H minus needs to react with positive. How many positive carbons do I have? 2 of them. Oh, crap. Okay. Well, maybe they only showed that hydrogen attack one of those positions and not the other. And if we go through and take a look at our answers, that would be not true. Okay? So they are showing us possible answers in both cases. So if we go through and flag those, there's our hydrogen. There's our hydrogen. So definitely going to the other position. There's our hydrogen. And there's our hydrogen. Okay, so they're showing the hydrogen going in at both positions. Okay. Well, is there something else I could evaluate on this that could help simplify my answers down? What about the deuterium?
3 of them are on the left side.
Deuterium is not more electronegative than hydrogen. Deuterium and hydrogen are both the exact same electronegativity, okay, and they are both less than carbon.
If aluminum acts like boron, would we want to see this in addition?
If it's acting as borane, it's acting as the borohydride. The borohydride didn't do a syn addition.
Doesn't want to go to the most substitute.
We don't even need to evaluate that yet. That's getting more into the chemistry. Where's the hydrogen going to attack? Say that again. Backside attack. Where should the hydrogen be relative to the oxygen? Opposite sides. There it's on opposite sides. There it's on opposite. Oh man, did this not work? Oh no, look at that. Uh-oh, same side. What does that mean? Not right.
Why
Same side.
you don't oh, that's
Because the nucleophile has to come in and attack from the back side.
and the oxygen don't move those two out because they kind of flip the oxygen to the other side somehow.
No, the oxygen, B and C are equivalent on sides of the oxygen. D and A are equivalent on the sides of the oxygen. I think I see where you're going with that. You have to be a little bit careful with that assessment because what could they do to the structure? They could flip the whole structure over. So just because the OH appears to be up, you need to be careful with that assessment. It does look like, I think they ended up drawing the enantiomer in that case and they didn't do a rotation, so you could potentially do that. Just be careful with that assessment. Okay? So, the question is now asking, where does the hydride attack? Does it attract the most substituted or the least substituted position? Why does it attack the least substituted? Why is it SN2?
Because you get a backside attack.
Epoxides will always do a backside attack. Always. It's actually the less positive carbon.
Would be less electron volt.
Steric hindrance. Why is steric hindrance important?
Well, wouldn't you want the oxygen to go into the less substitute?
Strong nucleophile. Strong nucleophile, bad leaving group. Strong nucleophile, bad leaving group, we attack the least sterically hindered site.
So you're saying H minus
Is a strong nucleophile, yep. And so it will attack our least sterically hindered site, which will be which position? The side with the deuterium. Deuterium is just heavy hydrogen, that's it. Why'd they include hydrogen, or include deuterium here? So you could tell the difference between your hydrogens being added, that's it. Okay? So your hydrogen needs to be on the side with the deuterium. What happens to the deuterium as the hydrogen comes in and attacks? It's going to toggle to go the other direction, and we end up with C is our final answer. Okay? You have the ability to process your way through all of these. Okay? Realize we are going through it very, very slowly. Okay? But we're asking those easier questions. What is the most active thing? Where does this attack? How can it attack? There are certain parts that you need to know, okay, to get through it. Of course there are. It's a chemistry class. Okay? It's any class. If you didn't need to know it, you wouldn't be taking the class. Okay? There has to be something new that you have to know to be able to process through it. Okay? When it comes to the addition reactions, one of the things that you should kind of keep in the back of your mind is you have not had a lot of time to practice them. Which means already, anytime you see an addition reaction, you are likely to get it wrong. Skip it. Okay? Move on to a different question, come back to the addition reactions later. Okay? The next part of sort of advice that I really don't like giving, but it's really the only thing left at this point, okay, is you need to know the reagents. Start memorizing those reagents. Practice through Saturday trying to figure out what's going on with each of these. Sunday, I would say it's no longer practicing and trying to understand, it's now memorization. Flashcards, here are the reagents, this is where the pieces go, this is what happens, done, move on. Okay? There's no, well, why does it do that? That game is over. Okay? That ship has sailed. You need to know the answer. Okay? So that when the final rolls around, if you hit an addition reaction where you're like, oh crap, I don't know anything that's going on with that, you immediately go, well, I don't care, I'm going to move on. Okay? And you can come back to it and evaluate it if and only if you have time. Minute and a half, roughly, you get per question. The instant you spend more than 30 seconds on a question, you have already got to have in the back of your head, I can get this answer right. If after 30 seconds you're like, I don't know, move on. Okay? The more time you spend on that question, the worse off you're going to be. Okay? Other questions?
It's kind of
Go ahead.
off topic, but is there any way to get that oxygen to the other side, like in B and D?
Well, there will always be another way to do it.
You just don't know off the top of your head?
Yeah, we'd have to change some significant structures to get that other product.
Okay.
Yeah, it's not just as simple as just saying, oh, let's just swap this around. Because, yeah, the larger issue is not so much the oxygen, it's the hydrogen being added on the same side as the oxygen is. That we can't do. So if we were going to get that set up, we would somehow have to have deuterium be our nucleophile. So you could do Li, Al, D4. And so deuterium would be your nucleophile somehow attacking. Yeah, yeah, those are problematic altogether because that only works for potentially B, but it doesn't work for D.
So as the atomic side is drawn, we can't do it?
True. Okay. Other questions? You legit have no other questions. I'm gonna- What's that? Number what?
Number 4 on the same section.
Yeah, and I got no problem just rolling through whatever. I need to hold that one again. Yeah, 4 is a mean one. Doesn't matter. It's actually completely irrelevant to the answer. So I will admit, every time I've looked at this question, I've panicked and gone, oh crap, I need to figure out how deuterium reacts. Doesn't matter. Completely irrelevant. So, they're saying, what is the possible product of the reaction show? Looking at those reagents can be kind of dicey. You could do potentially substitution or elimination. So I don't know, which one is it? I don't know, look at the answer choices. What do the answer choices tell you? It's elimination. Okay, so that clears up some information. So I know I'm doing an elimination, but what mechanism?
It's a strong base.
It is a strong base because of that negative charge, which means strong means 2 type. It's not SN because it's elimination. I'm doing E2. Okay? When I do an E2 elimination, what is the big complication that I need to know from it? I have to have an anti-alignment of the leaving group to the hydrogen that's removed. Okay? The hydrogen or deuterium. Why or? They're the same thing. Okay? So let's go through and look at our structure. Identify the leaving group. Where's the leaving group? The bromine. Okay, if I'm doing an elimination, the hydrogen needs to be removed from which position? The anti position, so anti to that bromine would be? Right here, CH3. What does that mean? They did not draw the structure in the appropriate alignment to get the answer swiftly. What do you need to do? You need to rotate about that bond to figure out what happens. I'm going to rotate it exactly in that direction. Let's see if I can do this. Oh yeah, it's going to be kind of hard. I'm going to have to look at the board. So I'm leaving the carbon with the bromine alone. As I do my rotation, I'm rotating the deuterium. Oh crap, I'm rotating it the other way. Sorry. Yes, I want to rotate it the other way. And we'll talk about why I'm picking that in a second. So I'm rotating it the other direction, which then means what is now in the plane with the bromine? Hydrogen is lining up with it. Okay, because I'm rotating it the other direction. So I'm taking that and I'm rotating it from that side clockwise. Did I do that right? Yeah, I did. I'm rotating it clockwise. Okay, so the hydrogen goes into the plane. The deuterium is now wedged. And the CH3 is dashed. When I do the elimination, I can take the electrons away from the hydrogen to form the pi bond and kick out the leaving group. The result is I form that carbon-carbon double bond. Okay, because it's all happening in one step, I get the CH3 going back, or hydrogen coming at me. On the other side, I get the CH3 going back, and I get deuterium coming at me. Okay, if I flip that on its side, the important atoms would be that I have a cis double bond. CH3s are on the same side, and I have that deuterium. So I go through and take a look at all my answer choices. Only one answer choice has the deuterium still in it, so that must be it. Oh, wait. That ended up with the trans product. Okay, well, I could go back and evaluate everything I did is right. Okay, so this is, again, one of those kind of pause moments. Okay, what do we do? Okay. What you might do is recognize that we don't have to remove the hydrogen. Could have removed the deuterium, which means we could go back and rotate. If you don't see that, that's fine. Look at your answer choices and hope something else jumps out at you. Like, say, perhaps, that the leaving group is still attached to the structure. That can't be a valid answer. Okay? At this point, you've spent well over 30 seconds, and you may not recognize that you can do another elimination. Come back to it later. Okay? You come back to it later, realize that we can do the rotation the other direction. And by doing that rotation, okay, again, I got to look at the board. What were we rotating? Yeah, we're bringing the deuterium into the plane. So we're rotating it backwards, which then means the CH3 is wedged coming at you. Okay, we're trying to push that deuterium that's behind the board down and around so that it becomes in the plane of the board, which means the CH3 is wedged, the hydrogen is dashed.
Will we be able to have our model fit or is it
I will answer that as soon as I stop recording. And what we would end up with is our double bond, where we have, and again you'll notice that I'm drawing this really, really ugly. Okay, because I would argue it doesn't need to look pretty. Hydrogen, CH3 dashed. One of those CH3s is away. One of those CH3s is towards you, meaning we have the trans double bond with no deuterium. B gets me the cis. That's not right. D still has the deuterium attached to it. That's not right. D is the answer. I don't need to know anything about how deuterium reacts differently from hydrogen, because as far as this question's asking, they're the same thing. We have to have the anti-arrangement of the leaving group and our hydrogen.
It's just there to throw it.
Okay. And the deuterium is pretty much there just to kind of mess with your head.
Yeah.
So you just pretend like deuterium's almost like a hydrogen?
Well, it is. So yeah. Yeah. What is the difference between deuterium and hydrogen?
An extra neutron.
A neutron. That's it. It doesn't change the charge, all it changes is the mass. Which you can have a mass effect come up in reactions, they rarely talk about it.
I was gonna ask, this mass effect reaction.
Yeah, it does, and I would have to spend some time to look it up. With 2 minutes left, I can race through one more question, if we got one more question. It's an annoying word to go in and throw, but they use it. So which bromide will most rapidly undergo solvolysis? Oh, this is fun.
Is it the circle one?
No, the circling is for some reason staying on the monitor. It's not on my computer. I can't get rid of it. Actually, here, let me try this. This is a lot harder than it looks.
Yeah, it's pretty-
Where is it? Where the hell is that 3? Okay, there we go. Sorry. Bless you. So, solvolysis and aqueous ethanol. Oof. No idea what that solvolysis is, but I know what ethanol is.
So it's sort of referred to sulfolysis or something.
So, with that kind of solvent, what kind of reaction would I expect? It is protic solvent. On the way. So protic means weak bases, which means protic, or sorry, one type reactions. So this is looking at SN1 or SN2, or sorry, E1. When we think SN1 and E1, what do we immediately think of? Carbocations. What is this question asking? Which one forms the carbocation? Why did they not ask that? I don't know. That's just what they did. So, which of those forms a carbocation quickly? Okay, why B? So what we're doing is getting rid of the bromine. Hopefully everybody's got that. And we are forming a carbocation at that position. What's going to happen to make that happen faster? Stability. The more stable that carbocation is, the better off we are. How can we stabilize a positive charge? Charge, they're all charged. Then size, they're all the same size. Then electronegativity, they're still all the same. Resonance. Okay. Do we have resonance options in any of these? Okay. I can have the double bond shift from the bond to the bond, resulting in positive charge here. Does that stabilize it or destabilize it? Stabilizes it, which means it's going to happen faster. Okay. B, no resonance, so A goes faster than B. C, D, ouch. Oxygen with its lone pair electrons. Sorry, I lost my pairs. There? Yeah. Gets us another resonance structure. Do we have another resonance structure for D? Nope, we're stuck. Which means A is our most stable. Okay. What does solvolysis mean? Solve means solvent. Lysis means breaking. Okay? We are using the solvent to break off the halide. Okay? So you can also see it written as hydrolysis, meaning water to break off your halide. Okay? That is also an example of a solvolysis reaction. Okay? We are definitely done.